Thank you very much. Hello, everyone. Okay, so let's see if I can make these slides go. Okay. Should I press something? Oh, good. Okay, great. So this is a presentation about AR optics. It's basically about waveguide technologies, but more of a deeper dive into 2D waveguides and more, I would say more importantly, 2D polymer-based waveguides, which is what we make. And I'm going to try to take you through, without it being a shameless plug for my company, a little bit of kind of general understanding on waveguides and the different types of waveguides. So, introduction. So why do waveguides matter? Why do we even care about waveguides? Well, if we don't have waveguides, we basically don't have an image, right? So we don't have AR. We don't have AR. If we don't have AR optics, there's no AR. And if there's no AR, well, then we're all out of work. And the problem with that is that we have some waveguide, currently we have some waveguide technologies, but they pretty much all suffer from some fairly major handicaps. But we think that polymer reflective waveguides, of course, they're not perfect, but they do solve a lot of those handicaps, okay? And a little bit of basics for those of you who are not optical engineers. What is a waveguide? What does it do? Well, a waveguide, quite simply, guides light from one area to another. That's basically why it's called a guide, a waveguide, light guide. Basically, light will come from a microdisplay. Actually, light will come from some kind of an illumination source, whether that be an LED, a laser source, okay? And then it will go through some collimation optics, okay? This is just a bunch of lenses, okay, that will collimate the light so that it will basically make the light parallel, because light's coming out of here in all different directions. Then you'll incouple that light into the waveguide, and this waveguide will guide that light to a certain area, which is what we call the extraction area or the outcoupling structure, call it what you like, and it will send that light to your eye. And the challenge here is that not only does it have to send that light to your eye, but it also needs to let in the ambient light, and that's the see-through aspect. Okay, and that's the basics. So what are the pain points? Why is this stuff so hard to make? Well, they need to be transparent, obviously, right? Because we saw that they have to let the ambient light completely through. So there needs to be some transparency. There is something called the eye box, okay, which is basically an area where you see the image. If you have a very, very tiny eye box, it's like looking through a keyhole. So the eye box needs to be fairly large to also accommodate for intrapupillary distance, because not all of us have the same distance between our eyes, et cetera, et cetera. We also look to the right, look to the left, et cetera, and we still need to see an image. We have to have color uniformity. We can't have, red on one side and blue on the other if we have a white image, so to speak. They need to be efficient, because obviously there's a power consumption issue here. These are smart glasses that need to run on batteries. They need to be bright for outdoor use especially. So we call that nits, okay, brightness into the eye. They of course need to not cost an arm and a leg. They need to be lightweight. They need to have a large field of view, FOV. This means a large image size, okay? We talk about angular FOV in optics. It's just how much of your field of vision this covers, okay? And of course, they need to be aesthetic. There's an aesthetic aspect because, we don't want helmet-mounted devices. We want things that look like normal glasses. These are all the difficulties and pain points. That's why this stuff's really hard. And that's why you see a lot of very bulky, ugly-looking smart glasses that are very expensive, that have lots of issues, okay? It's hard. It's really hard stuff to nail down. And then what are 2D waveguides? So how many of you have heard of 2D waveguides? Okay, great. Not all of you. So you guys can tune out, but for those of you who don't know, 2D waveguides are kind of the state of the art in waveguides. And quite simply, what are they? Well, they actually expand the pupil in two directions. Remember I said that there was an extraction structure here, okay, that extracts the light? Well, it also expands the pupil, okay, in a certain direction. And 2D waveguides actually expand the pupil in two directions. Why is that important? Well, here you have a 1D pupil expansion waveguide, and you can see that the optical engine is quite large. The pupil is only being expanded in one direction. In the other direction, you need that big, huge lens. 2D waveguides, what they do is, since they expand the pupil in one and then two directions, you can have a much smaller optical engine. That's of course great for weight savings. That's of course great for aesthetics, et cetera, et cetera. So 2D waveguides actually solve a pretty big problem in terms of, making these things compact, lightweight, et cetera, okay? And so they actually solve these three pain points. They actually give you a large field of view because they're able to expand the pupil in two directions instead of one. They reduce the size of the optics and they decrease the weight. But what about all this other stuff, right? Those are still some pretty difficult pain points to solve. Well, let's see what happens. We have various waveguide technologies that can address some of those points, okay? And actually there's two families. If you want to split these into two major families, there's diffractive and there's reflective waveguides. And diffractive is basically, works on the principle of diffracting light. These are diffraction gratings or holographic elements. And then you have reflective or geometric waveguides, which work basically on the principle of reflecting mirrors with prisms or, actually mirrors. Okay, and it's the basic difference is the way that light is incoupled, expanded, and extracted. They do the same thing. They're both waveguides. They both do this. Okay, it's exactly the same thing, except instead of having here, for instance, an incoupling and an extraction made with diffractive gratings, you'll have reflective mirrors. Okay. So hopefully that's clear. We'll do a little bit of a deeper dive there. So how do diffractive waveguides work? Well, they work on the principle of diffraction. It's not an optics course here, but if you know what diffraction is, basically it's when light encounters a slit, for instance, right? You've all seen the slit experiment. It diffracts because light is both a wave and a particle. Well, that's the same principle that they're using here in order to guide the light to where you want it, right? And here, there's two different types of diffractive structures. There's the SRG type, or slanted surface relief gratings, okay? And there's the holographic optical elements. They work very similarly, and they're both diffractive technologies. Some of them are either by nano imprint, fabrication is done by nano imprint, etching or lamination of these diffractive structures, or sometimes they'll laminate the whole hologram onto the waveguide. And these diffractive waveguides have shortcomings. Well, what are those shortcomings? Basically, they're linked to the fact that they use diffraction. And when you have diffraction, you create what's called the rainbow effect, right? So it's like if you've ever seen a CD, right, or a DVD, and you see like the rainbow reflected on the CD, that's diffraction. And that's what these things suffer from intrinsically. So it's very difficult to solve because it's intrinsically the way that the technology works. And they're low efficiency, right? It's because there's a lot of light losses because they're only optimizing certain diffraction orders, right? Again, without going into much detail, there's different orders of diffraction. You can't optimize for every single one, so you'll have light losses based on that. You'll also have something called eye glow. In other words, part of the light is lost this way, and it's not entering into the eye. That's also an aesthetic issue, right? because the person who's wearing these will look like a cyborg. We call that the cyborg effect. They suffer from a color non-uniformity, so the light path is slightly longer or shorter depending on the wavelength. So R, G, and B are not treated the same way when you're treating different diffraction orders. And of course, they're quite costly and complex. That's debatable, right? The diffractive guys will tell you, no, they're cheap. Well, it's kind of difficult to manufacture these. They have to be very, very precise. We're talking about nanometric structures, right? That have to be either imprinted or etched onto glass substrates, okay? And there's multi-layer, wafer glass, which again makes things more complex, but still doesn't entirely solve some of these issues. So, for us, there's some big showstoppers here with diffractive, right? There's the rainbow effect, which it's not very, you don't want an image with red over here and green over here. And it's not only the image, but it's any kind of ambient light that comes in can also get diffracted and you can get rainbow effects. It's low efficiency. This for us is a killer because we're all targeting battery-powered devices that can run all day. If we're thinking about a consumer device, we can't have huge batteries on these smart glasses or a huge battery pack. And then, of course, there's the eye glow. This is an example here. I'm not picking on our our competitors, but I'm not sure who this is. I think it's Vuzix, but you can see that that you could see like a blue kind of glow around the eyes, and that's not really great. So we have the other family that I talked about, the reflective waveguides. The best known reflective waveguide is Loomis, okay? Probably a lot of you have heard of Loomis. They are making a reflective waveguide, but it's based on glass, okay? The big difference is they're taking, I think it's 25, 30 pieces of glass, they're coating them, they're gluing them together, cutting them at a slant, and polishing the whole thing, and they make a waveguide out of that. Well, that's great, that works, no problem, but there's a different way to do it, and the other way to do it is to actually mold these structures in plastic, okay? And that's where the polymer comes in, right? It's a reflective polymer AR waveguide. And, some people say this is the holy grail. Well, actually, it solves a lot of those pain points, right, that we talked about. It's lightweight and safer than glass. It's very scalable because you're molding plastic, right? What's more scalable than molded plastic? You're not cutting and slicing, umpteen pieces of glass together. It's boom, you mold it in one shot. It's highly efficient. It's a highly efficient architecture. It doesn't suffer from the light losses that the diffractive waveguides suffer from. There's no rainbow effect and no eye glow because, again, we're not using diffraction, we're using reflection, okay, as the principle. And we have something at Optinvent called the Aura Lens, and this is a waveguide that I have here that I will show you. It exists, and we are making these today. Okay, and that's a molded polymer waveguide. It's molded in plastic. All the structures are molded. It's what we call monolithic. We're not gluing 30 pieces of plastic together. We're molding it in one shot. We are coating it, of course, and then we are gluing another layer on top of it. It's actually two geometric opposites of the other in terms of the structure, and that's it. And then you get a waveguide. So I think I don't have to make the point that that's much easier to manufacture, or let's say it's not easy because otherwise everybody would do it, but it's more scalable, right? We can do millions of pieces. It's a molding technique. It's it's not something where you have to invest billions of dollars to have an exotic new process. We have a field of view up to 50 degrees. Okay, we have currently designs that can do 50 degrees field of view. It's 85% transparency. As you can see, this is an actual waveguide, and it's transparent. I mean, it's pretty much see-through. You can kind of see the structures if I hold it up at a certain angle, but when you put it in front of your eye, you can absolutely see right through it. It's highly efficient, so at least 3 to 5 times more efficient than a diffractive waveguide, and it could actually go up to 10 times more efficient depending on how the diffractive waveguide is implemented. But we try to be conservative here and not just throw out numbers, so we're going to say 3 to 5 times more efficient. And what does that mean? So just to throw out some numbers, we can go up to 20,000 nits per watt. So for some of you who know a little bit about how these things work, that's pretty huge, right? So to have a good usable outdoor device, you need about 3,000 nits, 3,500 nits, and we're able to crank out to 20,000 nits per watt of power consumption. And again, I should qualify that. That's based on a certain type of optical engine. It's a LCOS microdisplay with LED illumination, etc. So that depends, but we can go up to 20,000 nits per watt. We think that that's kind of best in class. And in terms of the eye glow, there's actually, there's less than 1% eye glow, okay? Whereas with diffractive, you have around 30%. Here you have less than 1%, so it's pretty much imperceptible. Okay, and there are no color artifacts, no rainbow effects. Okay, and so yes, these reflective polymer waveguides solve a lot of these pain points: color uniformity, efficiency, brightness into the eye, cost, and of course the 2D solves these. So what's left? It's transparency and eye box, and all the waveguide technologies are pretty much the same there. So there's no magic formula there, but we think that the reflective polymer waveguide solves some of these really key pain points, okay? And in terms of the Aura lens architecture, how does it work? Well, it's a 2D waveguide, just like I showed before. You have the first pupil expansion done here. Well, sorry, you have the incoupling, first pupil expansion, second pupil expansion, and that's it. Here you have one of the 2 pieces that I talked about, right? So this is a 2-piece system. It's 2 pieces glued together. This is 1 piece, so you see the prisms really well. When you glue them together, it becomes transparent, obviously, when you bond them together. But for demonstration purposes, there's 2 structures here. One is the first pupil expansion. The second one is the second expansion and extraction. Okay? And it's as simple as that. These are the 2 pieces I'm talking about. One is the geometric opposite of the other. They are bonded together. There's a coating in between, and that's how it works. Okay? We'll have time for questions later, if need be. And so what are some of the key breakthroughs that enabled this? So, and why didn't anybody do this before? Well, because it's, we now have very high index and very low birefringence injectable polymers that we didn't have before. So there's a lot of material science that actually is allowing us to do this, right? And then precision tooling and injection molding techniques have come a long way, which also allow us to do this. And we actually have adapted, we have a proprietary process that is used for making our Aura lens, which is super top secret. And it's allowed us to make the plastic with the levels of accuracy and tolerances that we need to make a waveguide. That's the key, by the way, is plastic doesn't really want to behave the way that you want it to. It tries to go all over the place, it tries to shrink, it tries to do a whole bunch of things. The key is to make the plastic do what you want, and we've found a very proprietary method to do that. And then, of course, advances in thin film coating on plastic. It's really actually quite hard to coat plastics and have the right performance, adherence, etc. So some of these advances have allowed us to come up with the Aura lens. However, nothing's perfect. What are some of the challenges of these polymer reflective waveguides, right? Because if there weren't any challenges, well, everybody would be doing it. So it has actually a larger footprint for a wider field of view than some of the competing technologies. It means you need more real estate. You need more physical real estate on these things to have a wider field of view. You need extremely tight tolerances. This is what I explained before. And I'm not going to throw out numbers here, but it's super, super tight. I mean, we're talking like aerospace levels of tolerances that you need, and we're trying to do that for a product that we're actually, you know, and I will throw out a number here, we can get sub $10 waveguide prices in volume, you know, with our technique. And so you're taking aerospace levels of tolerance and making them very, very low cost for consumer products. That's the big challenge, right? Because yeah, anybody can make these in a lab, you know, use a diamond turning machine, but we're actually molding these with kind of crazy levels of tolerance that is required. And then of course durability, right? It's plastic, so it's going to be less durable than glass. Of course you can hard coat these, okay, to make them more durable, like your ophthalmic lenses that everybody wears. They're made out of plastic and they have hard coatings. But intrinsically, you have to treat these a little bit special when they come out of the mold, when you're handling them, etc., because they are quite prone to scratching. They are, you know, there's some UV and thermal issues that, again, can be solved with coatings. Performance snapshot, so I'm not going to go through this in detail, but, you know, versus diffractive, you know, in terms of efficiency, it's much more efficient. Much lower cost, no issues with rainbow, and no eye glow. Okay, and if we look a little bit into the future, we can think about 3D waveguides, okay, and meta surfaces. So that's probably the next breakthrough that we're thinking about. Use of ultra high index materials, so even beyond what's available today. So, you know, with 1.76 index of refraction and beyond. And of course, precision 3D micro optical printing is, you know, an area that can also be explored to get super precise polymer parts. And that's pretty much it. So, we have about 4 minutes for questions. Yeah.
Does anyone have any questions? You can use that mic to answer. I'll come back to you.
Is this on? Okay.
Hello. Yeah, thanks for the talk. I'm interested in the coating technique because I understand it for the Lumos reflective waveguides, how they have these different coatings, but I can't wrap my head around how you would be able to do that. Can you explain maybe a little bit how you can do that?
That's an excellent question. So, contrary to Lumos, I think what they're doing, again, I'm not, we don't necessarily reverse engineer Lumos's waveguides, so we don't know, but we can theorize that they're using different coatings for each, right, for each structure. We're not, actually. Depending on the field of view, we either have one zone or two zones. That's how we're solving it. However, it's a little bit trickier than that. So we also need to make sure that the coating only goes on certain facets. So we have a proprietary process to do that as well, to make sure that the coatings are only going where we want them to. That having been said, they're not 30-layer coatings, okay? These are still fairly industry standard dielectric coatings. But thank you for the question.
Hi, I'm not in this field, so I don't know anything about the hardware, but you say it solves the field of view problem versus diffractive waveguides. I was just checking, it seems like that, for instance, the Snap spectacles, their waveguide gives you about 46 degrees of field of view, and you say you got to 50. Mm-hmm. That doesn't seem like a big difference to me. And what's the kind of the theoretical limit of your technology versus diffraction?
So another great question. So my point wasn't that the polymer 2D waveguide solves the field of view issue. It's that the 2D gives you a higher field of view versus a 1D. Okay, that was it. So both the diffractive, the Lumos, ours, it's pretty much the same limits. Okay, there's a there's a limit on field of view based on real estate. You can't have a lens that's, you know, that's this big. You need to have it that's, you know, that's the limit. theoretically, we can go to 100 degrees, but then we'd have a lens like this, so and nobody would want to wear it.
Thanks for presenting that information. It's really interesting. Have you thought about how to tackle prescription correction for those who require it?
Sure, another excellent question. So it's really simple for us. The prescription just will go behind the waveguide. So there's no magic there. You'll need to put a prescription lens behind the waveguide, and it'll correct for your vision. We don't correct for vision within the waveguide. One other thing I will mention, though, so thank you for bringing that up, we're able to adjust the focal distance of the waveguide by design. Not dynamically, okay, but by design, we can put it at 2 meters. And we don't need a push-pull lens. So with a diffractive waveguide or with a Loomis waveguide, for instance, you'll need a lens in front and behind to put the focal distance at, let's say, 2 meters. We don't need that at all. We can do that intrinsically within the waveguide, put it at the distance that you want, and then if you need correction, yes, we need to add a lens. Yes?
How do you control the brightness uniformity for different fields of view with a single coating?
Excellent question. Because we have a great engineer, his name is Yao, and he's sitting up front here. But yeah, it's an optimization that we do with a certain coating recipe that has a certain spectral response, and it's a trade-off. And like I said, depending on the field of view, you might have 1 or 2 or multiple zones that will assure that you have a fairly good brightness uniformity. But it's a trade-off. It's a trade-off. It's a cost versus, brightness uniformity trade-off. The more zones you have, the more complexity, the more cost.
Thank you.
Thank you. We are taking a 5-minute break before the next session now. So yeah, you can stay for the next session, or if you want to go somewhere else. Thank you so much.